Assalamualaikum. Today we are going to discuss about Chatellier's principle. Imagine that you are trying to walk on a tightrope. In order to walk on it, you have to be able to balance yourself. Now, there will be some outside factor that will disturb you along the way, such as wind or some heavy load. Now, these disturbances will sway you either too much to the left or too much to the right. Ultimately, will cause you to be imbalanced. To keep yourself balanced, you need to respond accordingly to the situation. If you were swayed too much to the left, then you have to pull yourself to the opposite side, which is in this case to your right hand side, in order to stay on course, and vice versa. Also, this response will happen spontaneously without the help of any outsiders, because your brain will automatically tell you what to do in order to. This analogy can be applied to a reversible reaction that have achieved equilibrium. Should any changes from the environment affect the system and making it unbalanced, it will automatically respond in order to re-establish the equilibrium. If the equilibrium is being disturbed by favoring the reactant side, the system will respond in the manner to achieve back equilibrium by shifting the reaction to the right. Thus, forward reaction will occur. Similarly, if the equilibrium is being disturbed by favoring the product side, the system will respond in the manner to achieve back equilibrium by shifting the reaction to the left. Thus, reverse reaction will occur. There are three factors that can affect the equilibrium position of a reversible reaction, namely temperature, concentration, and pressure or volume. Let's discuss the effect of temperature. The response of the system upon the changes in temperature will depend on whether the reaction is exothermic or endothermic. So it is important for us to know if the delta H is positive or negative. Remember that the delta H shown in the equation is always belongs to the forward reaction. Therefore, if the equation is written like this, it means that the forward reaction is endothermic and the reverse reaction is exothermic. Since forward reaction is endothermic, this means that the reactant absorbs heat in order to make product. Therefore, we can consider heat is a part of reactant. If the equation is written like this, it means that forward reaction is exothermic and reverse reaction is endothermic. Since forward reaction is exothermic, this means that the reactant release heat along with the product. Therefore, we can consider heat as a part of product. Let's consider the first scenario, where the delta H is positive. If temperature is increased, that means more heat is added to the system. The system will respond by using up the extra heat. To use this heat, the system will undergo endothermic reaction. Since in this case, forward reaction is endothermic, therefore equilibrium position will shift to the right. Similarly, when temperature is decreased, that means heat is taken out from the system. System will minimize the change by generating more heat to make up for what it has lost. To release heat, the system will undergo exothermic reaction. Since reverse reaction is exothermic, therefore the equilibrium position will shift to the left. The opposite response will be observed when you have reaction with negative delta H. Again, when temperature is increased, system will respond by favoring endothermic reaction. But this time, since reverse reaction is endothermic, the equation position will shift to the left. And if the temperature is decreased, the system will respond by favoring exothermic reaction. And because forward reaction is exothermic, the equation position will shift to the right. Let's take a look at this example. Here we have a system at equilibrium between hexa-aqua-cobalt ion and chloride ion as the reactant, while chloro-cobalt ion and water as the product. Hexa-aqua-cobalt ion is a pink color solution, while chloro-cobalt ion is a blue color solution. According to the equation, the forward reaction has positive delta H. At room temperature, the solution appears purple. It indicates presence of hexa-aqua-cobalt ion and chlorocobalt ion at equilibrium. The solution is then put into two different conditions. One is in an ice bath, while the other one is in hot water bath. After 10 minutes, the solution in ice bath will turn pink, while solution in hot water bath will turn blue. This is what happened in hot water bath. To counter the increase in temperature, the system responds in the manner where the reaction will use up more heat. Since forward reaction is endothermic, therefore the equilibrium position will shift to the right to be re-established. Therefore, the solution appears blue. The opposite happens in ice water bath. To counter the decrease in temperature, the system responds in the manner where the reaction will generate more heat. Since reverse reaction is exothermic, therefore the equilibrium position will shift to the left to be re-established. Therefore, solution appears pink.